is, you can have latent class models where you assume that it's not continuous, but it's a discrete grouping, kind of like the Poisson model we talked about, the zero inflated. That's kind of a latent class where you're either a person that has no probability of event or no possibility of an event, or a possibility, and I don't know which one you are. So you could introduce that, and of course that can have different levels. Latent class are often used in education models. Try to capture like groups of types of children, kind of thing, from testing results. As various ways it's used. We're not going to do latent class except for just mentioning the zero inflated Poisson. So we'll condition on some continuous characteristic that we assume is randomly drawn from the population when I draw the person, and then we assume then the outcomes are independent of each other when I conditional on the covariates and whatever this latent variable is. And that allows us to draw our likelihood like a product. So this comes next after we discuss G. Just to point out, they're not mutually exclusive. You can have a transition model that's a mixed model. You can have a transition model that you're fitting with GE. Like they're not necessarily mutually exclusive. They can be combined. And just to re-emphasize this point, fitting these models doesn't guarantee you're separating out the actual longitudinal effects from the cross-sectional effects that we discussed before. That's more of how you fit the regression model to find it, not so much the likelihood or the method to estimate the coefficients. So this is always important to remember. This is a little bit early to introduce this, but we're going to use another simple data set. This is just continuous outcome data on dental distance, so looking at like how the distance between teeth grows when you age as boys and girls. And that, I think it's used for braces, like when it's a good idea to get braces when you peaked. Anyway, it's convenient. It's a small data set, and it's got this nice repeated measure structure, longitudinal. I could just say I want the difference by the end of 14. What is the mean distance for girls minus the mean distance for boys at age 14? But I'm going to use the slope to fit it. So I'm not just going to take the observation at 14. I'll use the whole thing, predict here, predict for girls, and compare that. That's something that makes sense regardless of how I fit the model. That's still something that will have a smooth sampling distribution. So that's the issue, is that when you don't a priori choose what you're going to report before you fit your model, then your parameter report becomes data specific, and you're not even technically, in reality, your sampling distribution becomes undefined. Sometimes you have this parameter, sometimes you have that parameter, right? You could imagine doing a bootstrap and trying to give it, because bootstrap doesn't work unless the sampling distribution is normal. So it gives you some idea. Sometimes 20% of the time I reported just an average slope, 80% I reported separate slopes. That may give you some more information. It's not technically inference, like a confidence interval. But it's always an issue. Like that's why causal inference is so compelling, because you specify a parameter that has nothing to do, it's non-parametrically defined. You're not defining it with respect to coefficients. It's like I want the mean here and the mean when everyone's treated versus the mean when everyone's not treated. And then I can fit the data the way I want to in that context, because my parameter isn't a function of the model I'm fitting. And that's the way a lot of the analysis is going, right? That's more and more people are saying, okay, I want to define something that has meaning that's separate from the model. And I want to be able to fit the models, not assuming any linearity, because who knows? Sometimes it's right, sometimes it's not. And so I get more robust, less biased estimates and more robust inference. The problem is, oftentimes they're black boxy, right? You get a machine learning algorithm that fits it. Then you say, typically what you do, this is like a rough idea how you might do causal inference. I would fit machine learning to this, including age and gender. So it might have all kind of complicated polynomials or trees or whatever. then I would say, okay, I want the effect of, let's say, I mean, this isn't a perfect intervention, but let's say I want an effect of girls, the impact of girls. So I change everybody indicator to 0 and predict the outcome at, let's say, at 14, based on the model, and get the mean of that prediction. Then I turn everyone to boys, so turn everyone Xij 2 to 1, re-get that prediction. Now I have the average of the outcomes at 14 when you're a boy versus a girl. I can compare them, right? The reason that people often are, I think, reluctant is people like to see a model, right? It kind of feels uncomfortable if it's a black box. Like some of these algorithms that you fit things with are, they don't really produce a model you can see. You can do things like variable importance that are post hoc examination of the model, these kinds of things. But that's kind of the bridge, that's kind of the gap we're at right now. So we need more diagnostics to make people comfortable with the black box and make sure it's correct. So it gives you some interpretability. So there's a big field of interpretable machine learning, or AI, that's trying to kind of solve this issue in some sense. It's not solvable completely. It's going to always be a little ad hoc, but yeah. So that, now in this case, everything, I could fit this non-parametrically. I wouldn't have to, I could fit it both interpretable and non-parametric, because it's all, I have ties at every age. I could get the mean dental distance for girls at every age and boys at every age, and I could make that my model, right? I could just say, okay, the mean of the outcome if you're a certain gender and a certain age is just based on the mean of that age, right? So in that case, when you can fit things non-parametrically, there's no issue anymore because it's both interpretable and I can't be more flexible, because yeah, that's the fitting the data. That's just fitting the data directly, right? All great questions. It's a little beyond the scope of the course, but I like getting them because I think they're important issues. And I really think we need a model selection course in the School of Public Health. I think it would be very helpful. Kind of try to would both talk about model selection and its pitfalls and how you could do it in a way where you pre-specify something of interest beforehand, but still fit parametric models, and maybe it goes eventually to teaching how to use machine learning to fit your models. So maybe in the future. So anyway, if we took this data, let's first start in the context of maximum likelihood. Let's assume, and we'll do that to show you how the estimating equation is evolved from the likelihood. So we have Yij is the outcome measure of the ith child at the jth time, and these jth time are regularly measured. We have two covariates, which is the age of the child, and we have the gender of the child. So the gender of the child is binary, arbitrarily 1 male, 0 female. It could be the other way. We'll fit the data exactly the same, or the coefficient would have a different interpretation. And so we'll assume some linear model with an interaction term. Why do I put that there, do you think? Why would you add gender times age? What does that imply? If this coefficient is not 0, beta 3, what does it imply about the slope for girls versus boys?
But there might be a different relationship.
Yeah, there's different slopes. That's what it implies. So it allows there to be different slope for girls, average slope for girls and average slope for boys. And of course, a test of that would be the test that beta 3 is equal to 0. If that was 0, then that would imply they all have the same slope. Yeah?
There, if, for example, beta is equal to 0, will that have an effect on the model if I've included? Or I could just...
Would it have
So my question is, if there is an effect, what is the impact or included or not including that particular element in the model, given that that is true or false? You know what I'm trying
Yeah,
to
I think I'm trying to. So, it's easy to answer that in the context of a priori specified. I believe there's interactions, so I'm going to put it in. You're asking, what if I have it in but take it out? Or
Yeah, exactly. So if I don't know if they matter and I don't include them, will that have an effect on the general
Yes, this is the point I made earlier in the course, exactly. If I look at this, if I take this particular data set, I do a test of that mean equal to 0, and I have a p-value that's not small. So, meaning it's big, so I don't reject the null, and I take it out. And then that would change what I report, right? Because now I'm reporting, let's assume if I report that, all I need to report then is the beta 1. This gives you a different intercept. So in other words, the slope for boys is beta 0 plus beta 2. The slope for girls is beta 0. But this has a slope for both. So if I had this in, I typically report the slope for girls separately from boys. So for girls it's beta 1, and for boys it's beta 1 plus beta 3, right? If I keep, well, depending on what I hold, yeah, it'd be beta 1 plus beta 3, because it's binary. And therefore, I don't technically have a sampling distribution anymore, because if I get a new data set and and repeated samples, if I theoretically took another group of children, followed them same number, same times, and then this time it was below 0, then I would report separate slopes. So it means that in repeated samples, I get different parameters depending on my data. And that's always a problem for defining your sampling distribution. That's why it's best always to say beforehand, maybe you want I could define something like the average slope. Even in this model, I could define it, right? I could take beta 1 and beta 1 plus beta 3 and add those together, divide by 2, that would be the average slope, right? And that would make sense regardless of how my model turned out.
Okay,
So that would be more likely to have a more normal type sampling distribution. If a priori said, all right, say I want to know the difference. Let's go back at another example. This is important, although. So again, we're going to fit this. This is our parameter. Just to point out, we're going to fit it with ordinary least squares, right? And I'm going to go over that in some detail. I don't expect you to memorize all the technical detail for it for sure, but just get the gist of it. So it can be motivated in two ways. One, if I specify a particular likelihood for the error term, when I have this plus an error, I can use maximum likelihood. It can be based on whatever I assume about the distribution of the error term. I can write down the density of the probability or the density of an observation given the covariates, and then I can solve the likelihood. I also can look at the OLS you get directly. You can show it's unbiased regardless of the distribution of the error term. So that's the estimating equation approach, where I'm just saying I'm not specifying what the error term could be. It could be, it could be symmetric. It could be slightly skewed. It only has to have mean 0 given the x. So what is max likelihood estimation based on? Is based on score equations. So you have to define the likelihood, right? Which is like in a cross-sectional case, you get the probability of the first observation times the probability of the second based on the parameters and the data. And then you take the log of it, and that ends up being a sum, right? Because if every observation is independent, the probability of them all is the probability of the first one times the probability of the second one, etc. And then we do classic calculus. I want to solve that likelihood. It's if theta is one dimensional, it'll look something like this. So this is the log likelihood. And this is theta hat. And you find the maximum likelihood, and that turns out to be your estimate, your maximum likelihood estimate. You can see it in one dimensions easily, right? I can just plot the likelihood versus theta, go to the maximum. Now there's ways to do, the computer can do this that you don't have to do it manually, right? There's ways of climbing these things to guarantee you at the top. In this case, it's even easier because I can just solve this analytically. I set this equal to 0. I want to find where the slope, that's the slope with respect to theta, where it's 0 because that's at the peak. And then I set it 0 and I solve for theta. That gives me a maximum likelihood estimate. In this case, turns out oftentimes you don't get just theta on one side and the data on the other. There's theta on both sides, and you have to keep on climbing up the likelihood. You can't solve it in one step, right? That's why sometimes when you do maximum likelihood, they'll see the iterations because you can't just do it in one step. But linear regression, it turns out it's an analytical solution. You can solve it in one step. So just, again, not terribly important, but just to get more tangible feel for what it looks like. So I'm assuming my error term is normal with mean 0 and some unknown variance sigma squared. If I look at my likelihood, it's just a single observation. If I'm and I'm assuming they're independent now. So just for one observation, this is the likelihood. This is the normal 0, 1 density. That's what that small phi always means, almost always. So and this is y minus the predicted value of y based on the current coefficients and the covariance you measure on that, the age and gender, divided by this. So this makes it a normal 0, 1. I'm taking y, I'm subtracting its conditional mean, so now that has mean 0, and dividing by sigma, so it has standard deviation 1. And so that is for one observation. If I take the log of every observation, first of all, if I take this for every observation, the likelihood is just the first one times the second one times the third one for every observation within every person, because I'm assuming independence now. We're going to generalize that, but that's what we're doing now. If I take the log of that, I get this. So this is the log likelihood. It's a sum of the log of the density, normal 0, 1 density, where this thing you can think of as just kind of the residual, right? This is observed minus predicted. And then this is the unknown residual standard deviation. Anyway, that's what it looks like. So what would you do next? I would take the derivative of that with respect to the betas. So I get the partial derivative with respect to beta 0, partial derivative with respect to beta 1, all the way through beta 3. And then each one of those gives me a different square equation for each parameter, set them all to 0 and solve them. And it turns out when you do that, you end up with matrix operations, but it can solve it in one step. It's analytic. So anyway, here's formally the maximum likelihood. Argmax means I'm finding the beta here, the vector of coefficients that will maximize the log likelihood with respect to all possible values of the betas. Again, if you don't care about the computation part, how it does this, you can just think of trying a grid over all possible betas, and it'll find the one with the highest likelihood, right? Sometimes that's the way you have to solve likelihoods. That's not common, but you have to just do like a grid search. In this case, we don't have to, but and if I'm just writing this out now, this is what it looks when I do that. Take the derivative and set it to 0, and then solve for beta hat. Well, not yet. It's just the same as this, right? So the log likelihood looks like this. And then just doing a little bit of algebra. So it's the sum of the squared residuals, right? I'm minimizing. Oh, it's just right here. Never mind. This thing is a squared residual. Right? It's the observed minus the predicted based on whatever betas that you're trying out squared. And that in itself is called the mean squared error. So you can think of this as maximizing the likelihood is minimizing the mean squared error. And that's ordinary least squares. I mean, that's what you're doing. That's why it's called least squares. Because you're minimizing squared residuals. I just put that in for this predicted based Yeah, predict based on the beta. So if you want to take, this is, again, just trying to make it more tangible if you care about the math, and it's just a simple regression of only two coefficients, and I can define my log likelihood, it looks like that. And then I take my score equations, I get 1 for beta 0, it looks like this, and 1 for beta 1, it looks like that. And you can show that the solution is this thing here. So in other words, I don't have to go through a search of the betas. I can solve these score equations directly, and I can get beta on one side and all the data on the other. And so I just plug and chug here, and that gives me my estimates. And the important thing is I can show that this is unbiased. So the expected value of the beta hats, in this case a beta 0 and a beta 1, is equal to the true values. And if I repeatedly did this and got my different estimates every time and took the mean of the estimates, that would go to the truth as I do this over and over again. So it's unbiased. So sample size gets bigger, beta hat will go to beta true, using the law of large numbers. So it's unbiased, and that's unbiased regardless. When you show that, it has nothing to do with the distribution of the error term, except the only thing it has is that the mean of E given X has to be equal to 0. But I don't have to specify its distribution. It's normal or whatever, and I still have an unbiased estimate equation. So then you can show, I might have motivated this to maximum likelihood, but I can use it where I don't have to define the likelihood anymore. I just treat it as an estimate equation. And this is the general way you can just treat them as estimated equations, and you can also don't rely on the distribution when you get your inference as well. And that's what's called robust inference. So we're not looking just at linear. We want this to be true for whether we're determining linear, logistic, Poisson, etc. So this is like linear, logistic, log linear. And meaning we can, again, I did this early in the course, but when I can write that there's, the important thing is G here is some link function, either identity in the linear case, I don't transform the linear part at all, logit linear in the logistic course and the logistic case, and log linear in the Poisson log linear case. So G is called the link function, and that's how we make sure the model is proper. It assures that is, no matter what I put in for the b's and the coefficients and the x's, I will get out a predicted value for the conditional mean that respects the natural bounds. In the linear case, there are no bounds. In the logistic case, it has to be between 0 and 1. Like the mean of a binary outcome has to be between 0 and 1. And the log linear case, it has to be 0 or greater. The general form of this looks like this. So you get the estimating equation for all of them. That's the general form. Don't worry about that. But it involves the derivative of the linear portion with respect to beta. Then you have the betas, and then you have the inverse of the variance covariance estimate. And because the way they do this is called iteratively reweighted least squares. That's how they solve the GLMs. In the linear case, of course, we don't have to do that because this weight is the same for everyone. They're assuming constant variance, for instance. So 1 over a weight that's 1 over sigma for every person means it doesn't do any different. It doesn't reweight them. So you can ignore that. It's for the binomial, 1 over the variance is the mean times 1 minus the mean. For Poisson, it's the mean, right? So these will change as you change your particular family you're looking at. But they all have this form. And that's why they call it generalized one of the reasons it's called generalized linear models, have a very general form for the solving the likelihood. And they all have this property that even when you ignore the distribution of the outcome per se, but use this, they're unbiased like estimating equations. So that's why you can use them to do estimation without specifying the likelihood. That's something else to say, but I've gone. Anyway, this is just a class. This is like a very, very very short. Oops. Why is it doing that? Of just generalized linear models. And this isn't the only ones. There's other generalized linear models that could fall in this class that have what's called an exponential form. But in a nutshell, for this class, this is tries to give you some explanation for where we're going now, where we're just going to use these forms of the score equations to justify an estimation where we're not going to worry about the joint distribution of the outcome, let's say. And we can do that because of the unbiasedness of these estimated equations. There's whole books written on GLM, including one called GLM. You're welcome to read it. I think it's kind of a waste of time a little bit, but because it's really not that. This is, I think, pretty much all you really need to know. There's things about, lots of stuff in like proving the concavity, the likelihood, and the guarantee that you'll find a maximum likely solution. There's, theory in there that's useful, but for the most part, practically, this is what it is. Okay, so now we're taking the leap that we really just ignored the fact that we have repeated measures and we'll have residual correlation, so the y's aren't independent, even though I can treat them way in the estimating equation, still get unbiased estimates of the coefficients. What we want to do now is modify how we get the inference so it accounts for it. Because we've already shown that if you ignore dependency between the outcomes and you just treat them independent, you get biased standard errors, right? So we have to fix that the way it's done in a way that's general and also doesn't add hopefully doesn't add as few assumptions as possible. So we get standard errors that are so-called robust. So here's the general form. These are all now like vectors and matrices. Don't worry about that. This is a general form for repeated measures. I can represent it as a sum across individuals' data. Remember, I is going 1 to m. So these things are, they're vectors of partial derivatives, and these are matrices. Now, it's not that important. It's just that I can have a general form that represents it this way. And now we have to, particularly we get our inference, we have to estimate this thing because the inference is a function of the variance-covariance model for the outcome given covariance. Or if you're in a linear case, you can think of the variance-covariance of the error term. So this messed up, but this right here, wow, this is really bad. Why did I do that? So is this better? Anyway, this should be shifted up, but whatever. So this is the variance covariance matrix for one, yi is a vector, right? So yi is equal to like yi1, yi2, all the way down to yi(ni). So whenever I do like a variance of a vector, that means it's a variance covariance matrix, just by definition. That means I'm getting the variance of a vector means you're a matrix where you have every variance of every yi and all their covariances, right? So it turns into a vector, a matrix. So this is ni by ni, the number of observations on a person times the number of observations on persons. It's symmetric. So like if I flip it over the diagonal, it's the same numbers. And along the diagonal, there's the variances, right? I have the variance of the first observation, the variance of the second observation. And then on the off diagonals, I have the covariances between them. Because now I'm assuming they're not independent anymore. So now the variance covariance matrix is defined by both variances and covariances. Just a note, I'm using this, it really is conditional covariance. It's after we adjust for the x's, it's the residual covariance. Anyway, I don't always use that notation because it just gets so messy, but so that's what I mean. This is the context of regression. I'm regressing the y's versus the x's, and I'm looking at the residual covariance between the y's given the x's. And that's not the same as the marginal if I don't condition on the x's. Here. So how do you get an estimate of this variance? Because we need it, as we showed earlier in another lecture, you need the estimate of this thing to get the standard errors. And again, in simple linear regression, that you would just do using the LM and R, or regress in Stata, where you don't tell it's repeated measures. It assumes something. It assumes the variances are all constant variance. It also assumes the covariances are all zero. And it carries through those matrix observations to get that estimate of the V, of the variance covariance of an observation given all the covariance measured at each time. So notice that the covariance, whoa, this thing is really acting weird. Okay, here we go. The covariance between two observations on a subject, I just picked the first and the second, but is equal to the standard deviation of one times the standard deviation of other times the correlation. So the correlation is the covariance divided by the standard deviation of one times the standard deviation of the other. It's a definition of correlation, okay? And the why that's important here is for GEE, it actually uses the family that you put in, whether it's binomial or Poisson, it uses the variance model. So it doesn't independently estimate the variances of each observation as separate from the model. But it assumes nothing about the correlation. So you can also get fully robust where it assumes nothing about the variances and the covariances. But the standard G implementation is what's called semi-robust because it does assume the variance model. And we'll learn about ways to even drop that assumption. But basically, so it assumes a variance model. That is, if you're doing linear, it assumes the variance is constant. When you're doing logistic, it assumes the variance is the mean times 1 minus the mean. When you're doing Poisson, it's the mean. And those are all model-based, right? So it doesn't have a separate way of estimating the variances there. You can do that. That's fully robust, and we'll talk about that, particularly when you get the apply part later. So again, if I have logistic, so again, just to remind you, because I know it's, okay, all right, can't find it. So again, just a reminder, we often think of logistic regression being a model for the probability, but with a binary outcome, the probability is the mean. right? The expectation of y is a proportion. So you can just, I just stick with the mean notation, but in case you're uncomfortable with that, it's the same if I put the probability of ij equals 1 given xij. So here, let's say this is my model here. And again, the linear part I always call m xij b. So it's a function of the covariates and the coefficients. The standard deviation by the model. So in other words, once I have an estimate of the mean, it's going to estimate the variance using this standard deviation here, which is the square root of p times 1 minus p, or square root of e times 1 minus e. And so I can write the covariance this way. So in other words, it's going to build this behind the scenes. You don't have to remember this. And then it's a function of these things which are known if the mean model is known. And then this part, which is unspecified. So this is treated as function of the mean of y given xij. And this is unspecified. Specified. And that's the way the process is separated out. So when it's deriving these variance covariance models, which it needs to get the inference after it's done fitting, it also it uses the known relationship between the mean and the variance in the model, and then it has also then separately estimates the correlation. And it does that on the residuals. So that's the way it forms. So you need an estimate of this thing in order to get that whole variance covariance. And it starts, before it gets to the inference part, it starts by allowing you to specify a working correlation, which means it doesn't believe it's true. It's just a way to get estimates that maybe are a little more using the correlation, the estimation part. So this is an important distinction that I should have made before. There's two kinds of correlation you worry about when you run GE. The first is a working correlation that you specify that's used in the estimation part. And then there's the non-parametric estimate of correlation, which it uses to get the inference. So you can do a model where it just assumes independence when it estimates the coefficients, but then accounts for correlation. I mean, when it gets its estimate of coefficients, but accounts for the correlation when it does the standard errors. And that's always important to remember at GE. It's got two forms of correlation. One is used in estimation, and then a separate one is used that doesn't assume anything, that is used to get the standard errors. Because it's going to plug in some version of that variance covariance matrix, and it makes no sense, just trust me, to estimate that non-parametrically when you're trying to get estimates. And in many cases, it doesn't matter what you put the correlation. Sometimes it won't have any effect in the estimation. Sometimes it will. We'll distinguish between those two. That's an important thing to learn for GE. And then afterwards, when it's got its estimates, it goes back and recalculates the correlation matrix, assuming nothing, so it gets inference that's not reliant on your guess, whether you guess independence or something else. And the working correlation matrices, since they're not really intended to get it right, they get perfect, they only give you a few choices. And oftentimes only one or two of them are relevant to any particular data set. So they're not an infinite list of these things in your GE function. They're usually 5 or maybe 4, and only typically some of them are relevant. And so that's what I'm saying here. At the end, you get a standard error, a robust one, that isn't based on assuming that working correlation you specified to get your estimates of the coefficients is true. It redoes it. So it reduces some bias in the estimate of the standard errors then, because it's not based on any particular model. So again, I can specify, you can't always do this, but in the linear case, I can specify my variance covariance for my whole data set. So this is like V of all y. So that vector, it's all my y's, all the y's from the first person, the second person, that goes all the way down to the last person. I can represent that in the linear case as sigma squared, remember it assumes that constant variance, times this block matrix. Every one of these entries represents not just a number, but a whole matrix. So R1 is the correlation matrix for observations on person 1. And R2 is the correlation matrix for person 2. And so they look like this. Here's Ri. The diagonals in a correlation are always 1, right? The correlation of a variable to itself is 1. And then the off diagonals are what you would think, the correlation between the first and the second, up to the correlation between the first and the last. So you place those in, the V's, as you go down, as it estimates things, either based on the model or at the end where we don't assume anything. And then the zeros, they're just block where they're all zeros, because they represent the covariance between two different people, and we always assume that's 0. And you have to specify that. Like you tell GE, oh, let this variable distinguish between different people, so it guarantees when it makes this matrix that it keeps the correlation among all observations between different people as 0. Right? This is all based on ID that you give it. So you put these all together, you get this. And again, we'll have situations where we estimate this in a simple way, where we're getting estimates, and then we'll re-estimate it where we put in non-parametric estimates of all those correlations. Okay. So here are some working models. This is the kind of things that you put in like, okay, let's just make a guess of what it is. The most non-parametric one is called unstructured. It's not completely unstructured in that it assumes it's the same model for every subject. And it's even going to give up that assumption later when it gets the inference. But now it assumes I'm just going to specify different parameters for everything. So correlation is always one. I just have separate estimated parameters for the correlation, the first and the second, the first and the third, all the way to the last observation. So this is sometimes you can use if you had balanced data. So everyone gets 10 observations. Maybe 1 or 2 are missing a few, but for the most part it's balanced data, you can use this estimate. You can use this as a working correlation to put in GE, and we'll show you how to do that. If I have really unbalanced data, so I have 3 observations in one person and 20 in another, and they're not measured at the same intervals, then this means nothing. The correlation of the first and second is totally different meaning for the first person and the second person, so it's no longer a possible matrix to fit. So you only can use this for very balanced data. And regimented time. Even if I had 10 observations in a person, but the spaces between them varied wildly, I would not expect them all to have the same correlation, right, between the first and the second. If there's 1 week apart for some people and 30 weeks for another person, right? So this only has really meaning with regular spaced balanced data. And it will only let you use it for that too. You try to use it, if you have unbalanced data, it will crash. This is the much more common. This is always the most common used form because it allows for correlation, but it's simple. It assumes every observation has the same correlation between any 2 observations on the same person. It was called compound symmetry. It's more commonly referred to exchangeable now, and that's what is referred to in R. So this I can use on any data. If I have 30 observations versus 2, I'm assuming the correlation between any pair on a subject is equal to the same value. So it's the most common used working model. Again, it's pretty strict, right? It assumes a lot about the correlation, so you wouldn't want to use it to get your inference where you don't have to. In inference, you can actually estimate things very non-parametrically, where you don't have to assume a certain form, the correlation structure. But for estimation, because it's not as sensitive to the estimates, except for in a couple contexts that we'll talk about, it still allows you to have some correlation. Maybe that can improve estimation, make it less variable, that kind of thing. It's usually taught as more a question of efficiency. It's different ones will give you, lower give you smaller sampling variability. And there's an important exception to that. We'll get to that, but that's when you read a GE textbook, it will tell you it's not important so much for the bias of the coefficient estimates. It's really trying to get efficiency. If you get it close to the truth, you get a more efficient estimate. You can inspire this from a simple, we've had this in a previous lecture, but if I have a simple random effects model, so that, I have E alpha I given Xij is equal to 0, for instance, I can, if I look at the correlation, so this would be the correlation of Yij and Yij prime, just two observations of the same, and J is not equal to J prime. It's equal to this. It's the variance of at the person level, the alpha I over the variance of the alpha I between plus within, which is the total. So it's, between over total variance is equal to the correlation in this case. So this particular model, we'll come back again, this is a mixed effects model. This particular one has an exchangeable correlation model. So there's one place where you do maximum likelihood, it's going to assume that's the right one. If you put in a simple random intercept like alpha I, it will essentially assume exchangeable correlation. But anyway, just one example. Another one for well-structured time series type data where, time-spaced and everyone has the same numbers of observations, like the dental data, right, where everyone's measured at fixed stages, could be autoregressive. So this is an autoregressive model. It's based on this underlying model. So this is how you sort of model the correlation of observations over time. If they're closer together, they're more correlated. If they're farther together, they're less and less correlated, right? So these are time. This would be like time 1, 2, 3, ... to whatever time in. So the correlation between person 1 and person n is this number rho raised to the n-1 power. Rho is going to be positive and less than 1. So the more you raise it to the power, the smaller it gets, right? It's equal to rho if it's only between adjacent observations. Any adjacent observations will have correlation rho. If they're 2 apart, it'll be rho squared. If they're 3 apart, it would be rho cubed, etc. So it allows for declining correlation within a subject of outcomes as the time between them gets longer. And it's based on a very common time series type model. There is a way to generalize this where you don't use, this requires that time is equally spaced. Again, you only have one parameter. It's like exchangeable. There's only one row to estimate for all of them to get that working correlation. You can have another one that isn't based on equally spaced. It could be unequally spaced, but you have to put the distance between them. So this one says the correlation is some function of the absolute value and the distance in time. So if I had time measurements, 10 minutes, an hour, 2 days, etc., it would assume the correlation is that rho raised, probably some constant here. I would guess there's some constant. It could turn into a 2-parameter family, raised to some absolute difference in the time, which allows for unequal time. I've never seen this used. I've never seen it work, to be honest. So I'm not sure how important it is. But in theory, you could use it as well. Again, for many cases, the choice of this is very small effects. And when the choice has a big effect, we have another whole complication we have to talk about, which is important but annoying. So for the most part, I don't think of this as a first order decision, but Okay, just a couple things. First, there was a mistake on the recorded lectures link, which I fixed. Thanks for letting me know. And so that's all up to date, and I'll continue to update that after every lecture. And then we're a little bit ahead of pace, which is great. I have a fairly short lecture today, so I'll probably get out a little bit early. And then on next, you'll have implementation GE lab today, which again is pretty straightforward. A lot of the stuff we talked about with regression follows is very similar to GE, which is just another form of regression. And then I'll do a little bit more implementation stuff on Tuesday, and then we'll go from there. So any questions before I get started? All right, we were here talking about, again, just to remind you, so GE has these two aspects where you worry about the variance covariance model. One where you have to choose a working correlation. And we've showed you various options, including this autoregressive and exchangeable independence, where you assume that they're uncorrelated. And this is just the correlation it uses to get that weighted estimate. It uses the inverse of the variance covariance matrix for an individual as a weight, and does the typical, solve the typical score equations for maximum likelihood, except for, of course, we're not doing full maximum likelihood because we're not specifying the joint distribution of the outcomes here. And then it has a second part, which is, okay, now it gets its estimates, and sometimes they'll be the same regardless of the correlation structure, and we'll talk a little bit about that, and you'll learn that in the lab today. Sometimes it can be quite different in the correlation structure. But then you have the second step, which is getting inference. And the inference part, they drop the reliance on that working correlation. They just re-estimate the correlation, assuming essentially nothing. And I'll give you an idea how that's done today. It's kind of a heuristic, but it's close enough to what the truth is. And then they get their robust inference. So, and typically when it's reported, you'll have naive inference, which is based on assuming the correlation model that the working one is true, and then robust, where it just drops that assumption and estimates the correlation non-parametrically. Again, there are two versions. There's semi-robust, which is what GE gives you, and there's fully robust. Semi-robust is where you assume the variance model that you chose from the family is true. So, and that means if it's linear, you assume constant variance. If it's non-linear, if it's logistic, it assumes binomial variance. If it's Poisson, it assumes Poisson variance. So all those are, in the normal case, it's just a single additional parameter, which is the residual variance. And the other ones, it's a function of the mean. So once I know the mean, I know the variance. And it uses the combination of that known variance and the correlation to get the covariance, right? Because those two together will define the covariance. And then there's fully robust, where you don't make any assumptions about the variance either. And I'm going to kind of present that again in sort of a heuristic way today. There's lots of ways, several ways you can derive the fully robust estimator. For I think one or two of you is in our 240A class, and you learn it from inference principles using the influence curve. It's been derived more analytically from scratch by Huber, who created the first sort of sandwich version of this. They're both the same. They just use different ways to derive them. And you also have the non-parametric bootstrap, which is another way of getting completely robust variance. It assumes nothing about the underlying distribution of the data at all. So, three separate ways. As I mentioned last time, generally, you'd always, even in the case of cross-sectional data, you always want to use the robust estimate of the variance. It should be the default in most stat software, but it's not. By default, they'll assume the distribution that you assume for what's implied by the model. So if you're in linear regression, it assumes normality and equal. That's not so important, but it's the equal variance it assumes. Logistic as well has built-in assumptions where there's no reason to assume them, because if the assumptions are true, robust variance estimator will go to the naive one. And if they're false, it'll be different. But one's correct, the robust one, the other one will be biased. So just a little tip that always better to do robust. If you're worried about reporting in a paper because people aren't as familiar with it, do both to make sure the naive is equal to the robust. Because if it's not, then you're reporting confidence intervals that can't be trusted. So again, we get a couple of examples here. We had other, but it's the options. Okay, I think I'm going to stop here. So what we're going to do next time, so I've talked about, again, it's not super intuitive, but you have the log likelihood, score equations. Those can be motivated to be estimated equations regardless of the distribution or the joint distribution of the outcomes. We've talked about working correlations and how they fit into that estimating equation. And then we're going to talk about next time, okay, after we just summarize how you get the estimates, just describing the algorithm, we'll talk about how do we get the standard errors post hoc? Because then we're going to have our estimates and we have to go back and re-estimate the correlation where we don't make these strong assumptions. And that's GE in a nutshell. So very much like standard regression with these couple bells and whistles to make sure you get your inference right and maybe you gain some efficiency by using a working correlation that's closer to the truth. And then I'll have an implementation lecture, so we'll go examples and things like that. Go ahead.
No, so in the GEE, what we
Examples earlier. So putting the pieces together, this is the way the algorithm works, if you care. You start by fitting them on. Do you go ahead? Oh, did it just go out? Or was it been
no,
off?
I didn't even.
Huh. Sorry about that. Oh, I wonder if I have it in here. I bet I have it here. Yeah. Yeah, there we go. Sorry about that. Anyway, there was nothing I was showing on the screen that was relevant till now anyway. So putting these pieces together, the way the algorithm works, let's just assume like you're doing linear regression, so linear version of GE. It first just fits a model, estimates the coefficients, assuming everything's independent. So just like a standard linear regression. And it gets those coefficient estimates. It uses those to get the residuals, including the residuals on each person. So people have repeated measures. It uses those residuals in the variance model to get the variance covariance matrix, and then it refits the coefficients again, plugging that in here. So it gets an estimate using the combination of your working correlation and your variance model to get this, which is essentially like a weight matrix, to get a weighted regression, gets your coefficient estimates, and repeats that process till conversion, till there's no change in the coefficients. So that's the way it works in practice, the algorithm. So even in the linear case, it's iterative in the sense that it needs an initial fit to get estimates of the variance covariance matrix, essentially getting that working correlation and using the variance model, plugs that in here. And generally this thing is equal to x. So the derivative with respect to beta is equal to the basis function. So it's like x times that, this typical score equation. And then it has its estimates. And then that's one phase. The next phase is, okay, now it has to get the inference. It has to go back and estimate this, no longer assuming the working correlation, but assuming nothing, to get the robust standard errors. So here's the kind of, I'll give you the sort of standard lesson you get in most papers or chapters on GE. If assuming typically they will assume when they teach GE that the mean model is the right form, which means the variance model is correct, right? No, not necessarily, but they'll assume the mean model is the right form. So your estimate of the variance based on that, assuming the family is correct. And the correlation model doesn't really affect the biasness of the coefficients, whether they go to the true value. It only affects the efficiency. So if you choose one that's closer to the truth, you get smaller standard errors. And that would be true if you have the true mean model. And that means, in this context, as sample size grows, all working correlations will lead to the same estimates. They'll all converge to the same numbers, the coefficient estimates. However, and here's the complicated part that's, when you get down dirty, things often get sort of ugly and complicated. If the model is not correct, not your working correlation model, but your mean model, then it turns out that each of these different working correlation models will give you a different projection. So if my mean model is not correct, it's going to fit through the data, and how it fits through that data is going to be a function of the weights I give observations. That's not true if it's correct. But even asymptotically, sample size gets big. If my weight model, if I use different weight models, I can get to actually totally different estimates. And that's because it's going to weight the data differently based on the relative sample size among subjects, how strongly things are correlated, how close your mean model is to the true model. So you get this confusing part where your mean model is not true, and that's almost never true, right? It can't be a miracle, it'd be true, almost, because you're just specifying an arbitrary parametric model. Your hope it captures the thing of interest. But if that thing's not true, then the choice of the variance of the correlation model, the working one, can change what you're estimating. It essentially weights the data differently. And I'll give you a simple example on the next page. So that's just one of these features. Whenever you weight something, you choose the weight. In some cases, it doesn't matter because your model is true. And if you weight, if my model is true, right? And so I'll put circles as big as the weight. If I have a weight here, here, the size of the weight, and I fit it, it's still going to be a line, right? Doesn't matter how I relatively weight. I could change the weights and ultimately it'll go right through that. As sample size gets bigger, if I fill in more and more data, it's going to go towards that line. However, if I have something like this, and the actual, here's my true pattern, and here are the weights. So big weights over here and small weights here. If I fit this one, it's going to go to this. Right? That's the best fitting line given those weights. If I do another one where same kind of pattern, but now I have small weights here and big weights here, it's going to go to this. I have different lines because the weights, you can think of the projection of this line onto this curve. That's the truth. This is the true. This is the best fit. That the best fit will be a function of the weights. And therefore you don't get the exact same, it's really get different parameters you can think of them as. So it gets subtle. How do you choose your weights? And we'll give advice. There's nothing like super rigorous to say about it necessarily, because it basically, we're talking about different weight or different working correlations defining different parameters. And it's like, how should you weight your data to get something that's close to the truth? I have a heuristic that I'll teach, but I wouldn't say it's necessarily objective. So, and we can see that in the next page. So this is similar to the example I gave. So this is just two different weight functions where I'm weighting each data point here differently at the exact age. So I have different weights here, or I have weights of 1. And if all the weights are 1, so I'm weighting all the data points equally, I get this line. If I'm using this weight function, so I have bigger weights down here, it pulls the line down, right? So you get different line fits. Now, if I fit that parametric model that could fit that curve, then as sample size grows, regardless of the weight, it would go to the true curve. But if I'm doing an approximation of that curve, that approximation is a function of the weights. That's a kind of important general thing to learn. That in this context, and typically when you learn, the weights just increase efficiency, but they actually change the parameter, change the ultimate values of the coefficients in our case, depending on what weight you choose. So it's not as simple as that. Most things are taught. When you learn like a classic linear textbook, or they always teach the theory assuming the model's correct. And because things are a lot easier. I don't have to worry about the weights changing the definition and how to now choose the right weight function based on that. But that's not realistic, right? Realistically, we can assume we're approximating some curve that we don't know. I mean, hopefully we get closer than these lines to that curve. But when we have high dimensions, you can't just picture it anymore. You can't just draw a picture that says, oh, that's not a good fit anymore, right? So it becomes harder to know. And so, then you need some way to choose, because you can get different answers. So that's just a complication. That will always be true. And that will be true when we get to, because mixed models will do something similar in their estimating equation. They'll also create a variance covariance matrix. That'll be a function of your variance covariance model. And in that case, it will be sort of similar. Different versions could give you different coefficients. They don't necessarily have the same, they're not the same things. They're different approximations depending on your variance covariance model. Now, there's additional complication. So that's one where the different weights can matter if in this case, the working correlations will result in different variance covariance matrices, meaning those are different weight functions. The only place it doesn't, even when your model's wrong, it doesn't matter typically when you're comparing at least the two most commonly, independence and exchangeable, so assuming no correlation to equal correlation in the working correlation, is that the data is balanced, it doesn't matter anymore. They give you exactly the same answers, because if everything's equally correlated and I have the same numbers of observations per person, it doesn't change the way that, relatively speaking, things are weighted anymore. So it'll give you the same thing as independence. So sometimes it won't matter, even if it's an approximation in terms of the estimation part. And again, we get our inference, we drop these assumptions anyway. When we're getting our standard error, it's a different process. This is just for the estimates. It's really the big change between working correlations comes when the data is unbalanced. So if the data is unbalanced and the data are highly correlated, the outcomes within the person are highly correlated, that's where you get the biggest difference between these working correlations. That's what really matters. And you can see, you can get differences where the confidence intervals don't even overlap. So that kind of contradicts the basic lesson, which is, they should all go the same number eventually, but they don't if your model's wrong and you have unbalanced data. So matters most. So what matters the most is you have these two scenarios simultaneously. And you'll see this in lab. You'll do an experiment where you have balanced data and then you'll make unbalanced data, and you'll see how the different weight functions, the different working correlations change your coefficients, just to give you some tangible feel for it. So one place that we compare this usually, because usually these are the two that we emphasize in this course because they apply to almost every situation. I can always estimate an exchangeable working correlation regardless if the data is unbalanced or not, because I'm assuming equal correlation of all observations, or independence, of course, working correlation, where I just assume no correlation when I'm estimating that, coefficients. If this is large, think of the extreme situation. I think that's a good way to think about it. So if the correlation among observations in a person, even after you adjust for the covariates, for the predictors, is still big, you still have lots of residual correlation. Well, let's say that correlation is close to 1, it's almost perfect. So if I know one observation, I know the other observations. And I fit these two different working correlations. Independence just weights all observations equally. Now that can be a little different, because if I have a family that has a variance as a function of the mean, then they will change a little bit the variance as the mean function. But let's assume I'm doing linear regression where it assumes equal variance. if I do this, it weights all observations equally. This, so that is, if I have a person that has 100 observations, every observation is weighted the same. So if I have one that has 5 versus 100, that person that has 100 weights 100 times more in getting the regression. They're 100 times more influential, or 20 times, than the one that has 5 observations. So you get a real difference in how people weight in how they contribute basically to the estimate of the coefficients when you use independence, right? If there's highly imbalanced, then you're going to have some people weighting a lot more than others when I do that. This changes that. So this, if the data is perfectly correlated almost, that means all people will weight about the same, because having repeated observations doesn't really add any much information because they almost have correlation 1. So this will tend to downweight people with higher observations and upweight people with lower numbers of observations. So it makes it more like I had a study that was balanced when I use exchangeable to get my estimates of the coefficients rather than independence, where it just keeps whatever in balance, and that's how it weights the people. It's a function of the number of observations per person. So generally, to me, that sounds like a better way to do it, is I don't want to get drastically different weights of people if for my underlying regression, if they tend to have lots more observations. That's not probably always true, but generally the data imbalance is a nuisance. It's not something that I want to get my inference based on. I'd like to get it more based on if I had equal numbers of measurements, and using exchangeable gets you more towards that if I have a situation where there's high correlation and unbalance. So it's another sort of rule of thumb is I always default to exchangeable if I'm choosing between these two, because if there is a big difference, their impact on the estimates, I want something closer to having equal numbers of observations per person versus having very different numbers where like a few people that have tons of observations really dominate the regression. And that is it's just a rule of thumb. It's not something that it could be given the way I want to do inference. I don't want to treat the repeated observations on a person any less if they have lots versus a few. And in that case, it's hard to come up with a case where that makes sense. But if that does make sense, then you want independence to get your estimates of your coefficients. And again, if the data is balanced, it won't matter. They'll give you exactly the same estimates. They don't change the weighting. These two different correlation structures. So I just say usually this is kind of what we want. We want to get estimates as if the data was balanced. Does anyone know how you would do this more rigorously? So I actually get an estimate that's based on, that weights people the same and not observations the same? What would you do? You could weight by 1 over the number of observations, right? Then if I have 1, I get 1. If I have 1 over 15, I get total of 1, because now it's 1. So you could add a weight, 1 over the number of observations per person, that would tend to downweight people that have lots of observations, upweight people, so that in a way that everybody contributes equally to the regression. I'm not saying that always makes sense, but that's one way you could do it. Right? Whenever you have this kind of imbalance, you could think of it as missing data. You can do the sort of inverse probability of missingness, which would end up being equivalent to doing 1 over the number of observations. So you could do that, right? In that you can always have weights separately to GE. It'll still do the other weighting part with the correlation. That's a separate external weight, and that would be one idea. So whenever you have missing data, you have two kind of choices. You can do imputation, right? And then, or you can do what's called inverse weighting. And imputation is you just fill in the outcome for a person that's missing. If I want everyone to have 15 observations, and let's say everyone's measured 15 times, and sometimes the observations are missing. So let's assume they have equal number of covariates per person. I can use some imputation model for the missing ones to impute what the outcome is, and then just do the regression on that full data, where now everybody has 15, or I can do inverse weighting, which is what I just described, where I re-weight people so people weigh equally towards the regression and not observations anymore. And weights can get more complicated. They're often used in causal inference because you want to weight by the probability that you got an intervention, let's say, things like that. So they're all coming from the same basic idea, which comes out of survey sampling, where in that case you have a known bias sampling. I'm oversampling people with a certain probability versus another group, and then you can get the regression over all the population as if it was represented in your sample, as if it was representative of the target population, where I want the representation of certain groups to be like it would be in that population. I can do inverse weighting. So big part of survey sampling when you have probabilistic sampling is this kind of inverse weighting. But again, it's kind of a missing data problem. You can just think of the way of handling missing data. As an ad hoc way, you can use exchangeable, and that gets you some of the way there. At least it's something in between independence and the more extreme form of weighting by the 1 over the number of observations. Okay, now we'll talk about getting the robust standard errors. I'm going to talk about how you get truly robust, because the basic mechanism is the same of how we get the semi-robust. So this is, does anyone use Stata here? If you use Stata, there's always a robust option, so you can always get the robust option for the standard errors. In R, there are packages that automatically give you back robust standard errors, but there's also packages that take the result of a regression, because that's all you need. You just need the original coefficient fits that you have, the coefficient fits, and you need the residuals, and you can build these estimators for robust standard errors. So and there's something called Sandwich package that does this in R, and other ones as well. So again, robust does not assume that what you guessed as the working correlation is the true one when it actually estimates the robust standard errors. It drops that assumption. As I say, it can be useful to compare the difference between naive and robust. So in a simple cross-sectional case, it's the standard errors versus the ones that use robust. It can give you some insight about how off the assumptions were for the use. But basically, if they're different, you always want to report the robust. That's just a general rule I'd like you to take from the class. It's like one way we should change practice is not use the naive estimators when we're using just standard logistic regression or linear regression. So again, I'm going to skip over this a little bit. I think it's a little gratuitous. We're just kind of showing the regression as a matrix operation. We're multiplying a vector of basis functions at the x's versus a vector of coefficients to get this thing. And again, I can represent it as all the observations on the person or all the observations total by just stacking all these things. So it's not that important. It's just how you can represent it as a matrix. Again, this is the most general form. So I'm looking at the variance covariance of one person. So this yi is, the yi is yi1, yi2, all the way down to yini. And again, whenever I say the variance of a vector, it means it's a variance covariance matrix. So the diagonals are variances all the way down to this. So the variances of each observation on person I in our case. And then these are the covariances. So these are the covariances between observations on the same subject. So again, it's because when they actually do these operations in the linear case, they solve the score equations using matrix operations. It can be somewhat easier to see what they're doing this way. I don't think it's that important. Again, ultimately, it has to create a big variance covariance matrix for all the data, so it just stacks these on top of each other. So all these represent matrices. That's a matrix for person 1. This right here is the covariance between person 1 and 2, and because they're different people, we always assume they're 0, so that's a matrix of zeros. I went over this in an earlier slide. So this is a big matrix that consists of matrices. This is how they actually build it to do the actual matrix operations. So you get one big matrix that defines the variance covariance of all the observed outcomes. And you can see whenever there's a 0 between in the covariance slot, that just assumes they're independent. That's what you're telling the procedure when you give it the ID. It says, okay, I can make this by assuming all the covariances of these observations are 0, and all the ones of these ones are defined some way within the V matrix. Of course, there's M people, right? There's M independent units, often people. So we'll assume that we're going to do this solution. This is the same as assuming independence, working correlation. Just the matrix version of what solves the score equations when I define this estimated equation. So we're going to assume if we use the working correlation of independence, we would get this solution. We've already gone over the fact that this is unbiased, again, for the coefficients. It depends on how to define what the truth is. Do I define it in terms of a working model or the true model? That's an issue I discussed. We're not going to go further in right now. And this just shows that it's true, and it's only true if in fact, I have the true model, but you can show that I don't have to, when I look at this, the distribution of yi doesn't come up. I can show the consistency, unbiasedness of this without invoking the distribution of the data. So, or anything necessarily about the variance covariance. So once you fit it, you want to get this estimate, right? That's how we get our standard errors, is we get an estimate of the variance covariance of all the betas. So we'll show what that looks like. That's what the procedure makes. And then it grabs the diagonals of those, takes the square root, and that's a standard error of coefficient, the intercept, the coefficient 1, etc. So if I just carry out this operation, the variance of this thing, which is the estimator, given x, ends up to look like this, which has this form. It's this thing, this thing. This is all data, right? The x's are just the data I have, so like the design matrix, so just the whole matrix of the x's where every row is a different observation. And then the only thing that's unknown is this, so I have to estimate that. That's that variance covariance of all the data, that v of y, right? This is that v of y bar. So it just technically has to plug in something there to get the standard errors. And that requires some assumptions, right? Well, first of all, we're going to assume that observations on different people are uncorrelated. That's always going to be an assumption. This doesn't work if we have everybody's dependent, all their observations. That's kind of a different class. That would be like, like network analysis or something, where you have one big pile of correlated data. We always have repeated units with repeated measurements in them, and those units are assumed to be independent. That's why we can use this approach. Now, if I assume it looks like this is, I want to derive my standard errors using this assumption. This is the standard naive form, right? So this is the naive estimates of variance. I'll say standard errors ultimately, by assuming that the variance of the outcome is that all observations are uncorrelated. So this This is, that's the variance of the first observation on person one, and this is the second on person one, et cetera. It's n by n, meaning it's all observations stacked together by all long, and then these are all the assumed correlation covariances, and they're assumed to be 0 in this naive version. So I'm going to show you what that looks like when I make this big assumption. So this is not robust, right? This assumes that the repeated measures are independent. And if it assumes that the variances are constant, right? That's an assumption. It keeps in the GE part that we're going to generalize here. Matrix here by one thing, which is this residual variance. I can use all the residuals for every person the same way, right? I don't have to estimate correlation of residuals within a person if I assume they're independent, and if I assume they all have the same variance, I can just borrow all the residuals. So how do you estimate these components? Well, if I only have one thing to estimate, I can define this to get an estimate of that. So, this is what we're trying to estimate under this model. We don't know what the error term is, if it's y equal ij equals, beta 0 plus beta 1 xij plus eij. We don't observe that, but we have something we can approximate it by, which is the residual. So once we fit the data, we take the observed minus the predicted value, and that, by definition, is the residual. So we can use the residuals now to estimate the variance component. And that's what the procedure does. It gets the residuals for every observation, in this case, and then it says, okay, well, what would I do if I observed all these things? If I observed all the EIJs for every person, from the first person, first observation, first person, second observation, all to the last person, last observation, I know they have mean 0. I can easily get the variance of it, right? Just get the sample variance, I'm done. In this case, the sample variance is the same as of just taking, since it has mean 0, right? The variance is variance of, I'll just say of y is equal to e y squared minus the mean of y squared. Since this is by definition 0, then if the mean of y is 0, actually let me be consistent. Of e is expectation of e squared times minus the expectation of e. That quantity squared, this is equal to 0, so it just is equal to e squared. So I could get my estimate of the variance then by just getting 1 over n I equals 1 to m, j equals 1 to ni, eij squared, right? That's an estimate of the variance. Now, again, you might do something like subtract degrees of freedom off. Don't worry about that. It's basically, I can get it by just getting, this is called the second moment. It's just would just be the mean of the EIJ squared. If I had that, that would give me my estimate of the variance. Unbiased, according to this model. That would give me the parameter I need. I could put a little hat on it since I got it from supposed data, the actual error term, and I'm plug that into that big matrix we just made. Now I have that variance covariance matrix, and I can plug that into the big formula and get my variance covariance for the coefficients. So the process goes, I have a form of the standard error, or the variance covariance of the coefficients, where I get the standard error from. Part of it's data, part of it's something that's unknown. I need the residuals to get that unknown part. Or if I observe the error terms, I could use that. I estimate it according to my model, plug that in, and that gives me the thing I need to get my standard errors. That's basically how the process works. The only thing is, of course, I don't observe these, so I'm going to do something similar, but plug in the residuals as an estimate of these error terms. So that's what I'm using. And this is basically how it would work in the naive case. They subtract the number, this is the number of coefficients, because it's slightly, it reduces bias. We all learn about sample it's interesting. It reduces bias. It actually increases the variance of estimation. Reduces bias. We always assume bias is more important, so that's what we do. But actually, not always clear that you want to use this rather than the one that doesn't adjust for the degrees of freedom. So this is something P is often called degrees of freedom. Anyway, you can ignore it. I don't care. It's really the average of the square residuals with the slight modification of the denominator. Once I get that, now this is something I can get from the data, so I've got that now. I can just make my matrix now, which is for every person, it's just that sigma squared times the identity. That just gives me sigma squared along the diagonal. And then I can stack all those up this way and get the whole, this is the variance covariance of all the y's. All capital N of them. So again, if I plug that in, remember we have this general form. This doesn't assume any particular variance model, but now we're plugging in an estimate or assuming a model. When I do that, things cross out and I end up with this. So this is what they report in standard linear regression. This is now this is the same as this. So it's naive estimate of there. That means you can get the first element of it will be the variance of the intercept. And I should put here, these should have hats on them. I'm sorry, they're estimated. And then that's the basic object you use to get your standard errors, right? So every time you do a regression procedure, behind the scenes, it'll estimate the variance covariance of the coefficients. This can be useful. The covariance can be useful when we do things like, I want to know the estimate of beta 1. I want beta 1 hat plus beta 3 hat. I want the confidence interval. It needs the covariances, so it goes back when I use like LinCom, it'll go back to this matrix and figure out now the standard error, and we don't have to do that ourselves. We can use those post-estimation commands, but it goes back to that. That's what it uses. And when it reports those standard errors in the column, it just takes the square root of these. So they're just the square root of each of the diagonals, gives you the standard error. It's a definition of a standard error. It's the square root of the estimated variance of your parameter estimate. That's what a standard error is. So that's the case. Again, algebra is not so important. The fact that it has this form in general, I make an assumption about the form of that. It allows me to define it by just estimating one parameter. I do that. Yeah, I get some simplification in this case. That's not so important. And now that's the thing that's plugged in. So we want to talk about, can I estimate the V a different way that doesn't make these assumptions? And it turns out you can estimate very non-parametrically. Here. You're applying a big matrix to another matrix and then applying it again, transform. It's like averaging all those elements of the variance covariance at the end. So that averaging essentially gets rid of the very large error that you get in each individual one. So in the end it works, and you have theory that shows it works. It seems almost ridiculous that it would work, but it does. And now you've built a big variance covariance matrix that assumes no model at all, right? It just takes the square residual for every unique observation, every unique person, and that's the variance of the observation. It takes any pair of residuals, multiplies them together to get the estimate of the covariance between any observations on a person, and it assumes no commonality between those forms. So this is completely non-parametric, and therefore it's fully robust when I plug that. So again, we've gone over this. If my model is wrong, I'm going to get bias standard errors, right? We know that. So if I have assuming independence among all observation, they all have equal variance is incorrect, then my standard error is going to be incorrect. It'll be biased. It could be biased high, it could be biased small. We don't know. That means confidence intervals won't have the right coverage, p-values will be wrong, et cetera, right? So it's important to try to get it right. And it's even better if you can get it right, which doesn't depend on the model, right? That's the whole point of this. So robust means it does not depend on the model. So we could still use OLS to get our estimates of this, our coefficients. That's using the independence working model, essentially, even when I have repeated measures. But I want to do something else to get this thing that allows it to just respect the data. It just goes back to the data, to the residuals, and estimates each of these components of the variance covariance I need one at a time based on the residuals. So we'll take a simple case to start with. We'll assume everybody has the same number of observations, like our general example. We can still assume a model, but now it will be unstructured. Now we'll assume everyone has the same model, but it's arbitrary with respect to the variance covariances. We're not assuming they're all equal or anything. And then how would we use our residuals to estimate that thing? And so this is like a different model. It's still not non-parametric because it assumes everyone has the same one. Truly non-parametric would allow every variance covariance for every person to be different. So it's a step between that and assuming independence. So in that case, this is the model part. This is the model assumption. Still not non-parametric. Which means I can borrow across all residuals across every observation to estimate the variance for the first observation and the covariance for the first and the second, because they all have the same value, whatever that value is, even though I'm assuming arbitrary. It doesn't necessarily go up or down with correlation over time. It's assuming nothing of that sort. Since they all have the same form, we'll just call it V0. I don't have to specify a form for one person, two person, they all have the same form. So we'll call them the same symbol. And then when we build it, once we estimate this thing, we could plug it in here and we have the same general form, right? So I'm just building a different V. Again, this was equal to the big V in the middle. It just means I have to estimate all these components from all the residuals. So if it's capital N, I need N plus N minus 1 plus N minus 2 all the way down to 1. Different parameters to define it. So how would it do that? So this is, again, we're going towards full robust. This is still naive, but it's naive based on a bigger model, right? It's not no model. So again, I just showed this earlier. Covariance of error terms is equal to, that's just the definition of covariance. Since these are both 0, the mean of the error is 0, it ends up to be that. So it's just, if I want to estimate the covariance, it's estimating the mean of one residual times another residual at a particular time. So the residual at J times the residual at K. And how do we get estimates of means? We take averages. That's all there is. So if I observe the E's, I could just take every person's jth and kth error term, multiply them together, and take the average across people, right? You only get one pair of residuals on the first and second observation, and one on the third, and the second and the third. So I would do this for every unique combination of residuals, take the average, and that gives me, again, I could adjust this for degrees of freedom, don't worry about that. And I get an estimate now of that component of the variance covariance. Again, not so important to understand, I'm just building it up. I'm going to plug it back in that big formula, and it gives me a different estimate of the standard error. Of course, we can't use the error terms, so we do the same thing. We get the residuals. So here's an estimate. This this right here is the covariance estimate of, I'll just say YIJ and YIK. That's what it is, YIK, YIJ. I can also do that for the variances, right? Because again, the variance is just what, if for the first observation would be the mean of EI1 times EI1 or EI1 squared, just like we discussed earlier. So I could get each unique variance by taking each unique residual for the particular observation and do that. And now I can build that model, right? So this is how you could, and then I could try that with, I could define autoregressive structure, and I could build that model using the residuals. That's how it works. Like whatever you assume in the model, it will use the residuals and use these kind of substitution estimators for these covariance terms, plug them in, build that, stick it back in, the equation for the variance covariance of the coefficients, and then carry out the operation. Back here. So in the end, it looks like this, right? I just put the average to make it, I built this thing. So I have the form of that V0 now, the one that's going to be always on the diagonal of this big matrix. I plug in the average of the residuals, the first observation on a person, take the average of the second to the average to the nth, little nth, and I get all the average of the cross products of them to get the covariances. So now I built this one thing. Now I can just plug this in with the appropriate zeros to get my big matrix that I plug back into the formula for the variance of beta hat, for the variance covariance of all the beta hats. That would be more robust than assuming no correlation. It would be more robust than assuming, it's more robust than that because at least it's a bigger model, but it's not perfectly non-parametric. That assumes that all these V's can be different from one another. How the heck would you estimate that? Because we only get one observation per person at time one, right? We don't get a bunch of different ones. So how do you get an estimate of the variance if we only have one observation? And it turns out you can get a really shitty one, but a shitty one that works when I plug it into that formula for the variance covariance for all the betas, because you can think of that as averaging out all these errors that I get. So the fully robust, which is the next step, which is for every observation, I just get my variance by taking the residual and squaring it. And I plug that in. And I get every pair of residuals on every pair of person, multiply them together, and I get my covariance. And so I build that big matrix now, which has different numbers for all the V's based on just using their, because this is an estimate of the variance. This is that estimate of the variance of YI1. And this is the estimate of covariance of YI1 and YI2. Again, not great estimates because they're based on one sample size of one, but we don't need each of them to be perfect because when you go back to the original equation, is that here? And so they all have, in the linear case, they all have that particular form where you're not assuming anything about the variance covariance. Based on your model, you have to estimate parameters of that variance covariance, so you plug them in once you estimate them on the residuals, and then you take that thing to get your standard errors. And of course, the less you assume about that V means the more robust your standard errors are going to be in the end. The less they rely on assumptions that may or may not be true. And of course, the bigger your model is, if you're not completely non-parametric, also probably the better it is, the less biased. Now, you can see if I have a very small sample size and I'm doing this, if I have a sample size of 10 and I'm constructing this matrix, I'm going to get very noisy standard errors. And that's why you often hear recommendations for GE that you should have a sufficient sample size. Because I want to average across all the people, I need a lot of people. So it's like this is an asymptotic procedure you would not want to use on a very small sample size. You need big enough so this robust isn't so variable that who cares about the bias? These standard errors are random variables. They can also have variance. We rarely talk about that, but they have both bias and variance. If the variance is huge, they become useless, right? And you can't trust the inference either. So this gives you some, at least, intuition why you need a relatively large sample size when you're going to when you want to trust the inference in these things. Again, GE isn't perfectly, it's not robust, it's semi-robust because it doesn't calculate the variance, it only calculates the correlation non-parametrically. And it uses the variance model. That distinction, it's good to remember in the back of your head. It's not important necessarily to understand mathematically, but it doesn't, in the case we just followed, it estimates the variance separately from the model, right? It's not estimating the variance as a function of the mean, it's just saying the residual squared. In the GE case, that's not true. They actually do assume the variance can be derived from the actual underlying family, whether that's linear with constant variance, binomial variance in the logistic case, and Poisson variance in the Poisson case. So again, in the binomial case, it will assume the variance is based on the model. It'll estimate these. These are the things it estimates with the coefficients. Now I can create the variance on that diagonal using the mean model, and I can get my covariances now by estimating the correlation non-parametrically. That's what it does. So it doesn't estimate the variance and the covariance. It just estimates the correlation, and it uses the variance model and the correlation to come up with the covariance. So again, technical, that does have some impact at times. Thing, and again, you can fit GE, and then you can get the fully robust sandwich estimator, which is what this is called, after you fit GE in a separate program. And we'll show you how to do that. Or you can do non-parametric bootstrap if you really want to be fully robust. I mean, generally GE does a good job. It's, unless your variance model is so misspecified by assuming the mean model, which can happen in Poisson in particular, you're generally okay. But fully robust is not the same. Fully robust, you need another procedure. So GE, the main stories were, one, it's really derived to estimate the conditional mean, just that regression part. It's not trying to, I can't use the results of GE to simulate data. It doesn't give me the distribution of the joint distribution of the y's or anything. I can only use it to predict the mean. It doesn't, when you do full maximum likelihood, like we're going to do with mixed models, I could use the results and the parameters, the underlying assumptions, to generate data from that distribution I estimated. Can't do that with GE because it only gives you back one component of that distribution, which is this mean. It uses the likelihood to define an estimating equation, in this case, which we went over, where it turns out that estimating equation derived from the maximum likelihood, the score equations, give you unbiased estimates of the regression, even if the underlying distribution that it was motivated by is not true. Working correlation model, basically if it's balanced, you don't care. If it's unbalanced, I advocate just using exchangeable, but the estimates will be different depending on which one you use, exchangeable independence or another one. And when they're different, again, you could think about doing other things like reweighting the data external to the procedure. The good thing is at least the standard errors are not dependent on the correct working correlation. If you don't know, anytime they say a working model, that means they're not assuming ultimately it's true. Working just means it's going to be a working model that maybe does a better job or something, but it's not specifying a true model. And then, of course, you can go one step beyond GE. In robustest. Of standard errors. So you can go one step beyond by not assuming the variance model. And there's ways to do that too. Okay, it's fairly, I know this is one of the more abstract lectures, sorry about that. I just want to give you intuition on how you build these things and what it means to get robust, and this will give you some intuition. More importantly, you'll start implementing them today, and I'll talk a little bit about implementation on Tuesday. And we'll see some of these concepts come back in the actual data analysis. So, any last questions? Yeah.
It's maybe tangential, but what is a moment? You mentioned this is the second moment.
Second moment is just the mean of a random variable squared. So when I select the mean second moment of EIJ or whatever,
Mm-hmm.
it's just the mean of that random variable squared. That's what second moment is. You can also consider the cross product too with the total. Usually that's what they do. Second moment. Third moment is the mean of random variable cubed, etc.
Okay.
And you can define, you can find the variance in terms of two moments, the first and the second, and covariance of the first and the second. Second then is a cross product, but still two things multiplied together. Okay, great. Thanks everyone.